sensor measurements are not going to be perfect either. Okay. Now, so here are the key questions, and I hope to answer these in the next 25 minutes or so. Okay, who should communicate what to whom? Parse that a little bit. So, what should I tell you? And who should I tell it to? And so, that's one thing. What is the minimum amount of communication? If everyone's silent, then I think we're going to have a problem in this. If everyone talks to everyone else, okay, lots of information flying around, but maybe too much. What's the best? What's the minimum amount? And how should you choose these gains? So I'm going to very quickly consider 4 cases here. And let me just jump straight into, because they all say something. The one I really want to solve is the bottom one, where everything is heterogeneous. Some people talk to some other people. Some people don't get to measure everything. Some people, they all see subsets, and everyone's subset is different. Let's start with the simplest case. Everyone sees everything that's going around. So you're in this room, you're looking at everyone else, you can see everyone, exactly what they're doing, but you're not talking.
Is your objective to optimize something?
Yeah.
Is a good performer, you think optimal performer or something?
Actually, everything I say is going to be, it isn't going to matter whether it's optimal in any sense, just that it's a state-based performance algorithm. So any state-based performance algorithm, but presumably for the spacecraft, I do be designing an optimal controller of some form. So let's say everyone estimates everything, but we only estimate on what we can see. But we can see everything, and so the full system is observable to everybody. So this looks reasonably good. We each have an estimation error, and I stack up this estimation error into a long vector, and I can write out the complete dynamics of the system. And I've written them out here. Now this is a very, very big matrix equation, because this one, just the first part of that, is the physical state. Remember, the physical state is where everyone is and where we're moving. Then everybody tries to estimate that. So if there are 10 of us, actually there are more than 10 of us here, but this is 10 times the size of this. Everyone's trying to estimate where everyone is, and everyone has some errors. So that's a very large matrix. And this is the dynamical equation for the matrix. This term here comes from the fact that people move as a function of what they're estimating. And then there's some disturbance noises coming in here. So the real question of how well this system performs is basically what are the eigenvalues of that matrix in there?
What is G again?
G is going to be a matrix of disturbance vectors coming into the system. So essentially that will determine performance but not stability. So let's just look at that particular matrix there and ask what are the eigenvalues. Now, it's not immediately obvious, but you can actually work out the eigenvalues in closed form if you take enough linear algebra. And I'll tell you what they are. The complete closed-loop eigenvalues are A plus BK, A plus LC, A plus BK plus LC, n minus 1 times. Now, this should look partly familiar. If you've got one estimator and one controller, you get A plus BK, A plus LC. That's the separation principle, which you've probably seen. Those are the closed-loop design dynamics. Those are the estimator error dynamics. So for one controller, one estimator, things work out exactly as you expect. When you put in multiple agents, you get additional dynamics. And if you have a look at these dynamics, they're not closed-loop poles, they're not estimated error poles, but A plus BK plus LC. That's actually the open-loop controller poles. And they're repeated n minus 1 times. So these are what I'm going to call disagreement dynamics, because these poles determine how the error in our estimates propagates through the system. So this is our design goal, what we want the closed loop to do. This is our estimated error goal, it's our Kalman filter, but these we don't design, we just get these. They're the open loop controllers. Now, you can only reach consensus if these controllers are stable. Now, you think, oh, that's not such a bad problem. Stable controllers? How common are stable controllers? They're pretty rare, actually. I would say 95% of the controllers running on the planet are unstable. You're not surprised? A PID controller is unstable. A PI controller is unstable. The most common controllers we have doing all of these processes are open loop unstable. You need to connect them to the plant. in order to get a stable closed loop. So you're not using a PI controller for this sort of problem. If you start chaining together multiple PI controllers, you're guaranteed to go unstable. And that's something that early control engineers realized, so they never do that. But anyway, these are the disagreement dynamics. Now let me give you a little simulation with 3 spacecraft just to make a point. Each of these is double integrated dynamics in 2 directions. I've magnified the noise, but I did an LQG control design, and I used a Kalman filter, and I implemented the Kalman filter. Now everybody here being the spacecraft gets to measure everything. So the blue spacecraft measures this relative position and this relative position in 2D. Same for the red one, these 2, and the green one measures these 2. So there's complete information, but no communication in the system. And they're running the Kalman filter, optimal, and they're running an optimal LQG controller. And when you couple them together, this is what happens. Now, this is starting to look a little worse than when I started off. And you can see now, if, say you're sitting here, imagine yourself sitting on this blue spacecraft watching these other 2. You say, wait, turn your algorithms on. They say, we're under control, it's you. You'd be a little concerned at this point. And I think probably at the end, someone hits you there. I'm sorry, it's not a full-blown simulation where you see the spacecraft into pieces. But basically, you're gone and they've disappeared off into deep space. So what happened there? Well, let me tell you about my design. This is the Z-plane. A plus BK are the eigenvalues of my closed-loop design, and they look pretty reasonable. Here's my estimator, IA plus LC, eigenvalues are here, here, and here. A little bit aggressive here, perhaps. But my closed-loop disagreement is here, and this one outside the unit circle is the source of the problem. So that's the controller opens, they're just unstable. So my estimation error, the mean estimation error I've plotted, and you can see 2 of the spacecraft, the estimation error just grows without bound. And the system goes unstable. And so there's a transfer function in there that is actually unstable. And it's not quite right there. It's the transfer function from the difference between the 2 noises on 2 of the spacecraft to the difference between their actuations is an unstable transfer function. And that causes the system to blow up because that instability couples into the others. Okay, so what's going on here? Now this is more like the meeting someone in a corridor. It's what my friend Sanjay Lal called second guessing.
So the first example, if you meet in the corridor, why would you go to instability if you don't communicate at all? Because you're just relying on your algorithm. So
how does it? Because your estimate of that relative position is not the same as the other person's. If those estimates were perfect, you would have an algorithm which would cause you to avoid each other. It's the error. It could be just initial error, or it could just be noise in there that puts it. And the thing is that when you do your optimal move, built into the design of that optimal is what the other person's going to do as well, because that was kind of a centralized controller. And it's the fact that they do something different because of the noise in their estimators pushed them over the edge, and that decouples. Once it blows up at one step, it gets worse at the next. So really what's happening is this second guessing, that when you update your estimate of what's going to happen next, the only information you have is your estimator. So what really happens is K1 times the estimate on spacecraft 1, Ki times the estimate on spacecraft I, Kn times the estimate on spacecraft N. And these 3, or all of these estimates, are slightly different. They've got different noise on their estimates, different measurement noises. But what you have to update is only your own one. Say you're the ith spacecraft, you think U1 is going to be K1 times Xi. It's not really, but that's your best guess of what number 1 is going to do. Kn times Xi is your best guess of what number N is going to do. So you update on your best guess of what everyone else is going to do. That's not exactly what they do. They use their own estimate here. They're all different. So it's this source of coupling and control that leads to these dynamics. Okay, now let's say we can fix this, because you can see this is second guess. You're not exactly sure what they're going to do. So the obvious way to fix it is everyone talks to everyone else. If I announce to everyone exactly where I'm going to go, and everyone announces to everyone else, then there's no confusion. We can sort this out. And actually, that's just choosing basically the input U and then putting in an appropriate gain here, which looks like the B matrix. And it's very easy to show. You get n copies of the Kalman filter out of this. You've completely eliminated all the confusion. You just have your designed Kalman filter dynamics. No problem at all, except the number of links you need is n squared. As n goes up, you need roughly n squared communication links. So that's maybe too many. So let's ask the question, what's the minimum? All right, now this is where the Laplacian comes through. Suppose we have a definition of the communication links in there, and now we're getting some communication in our estimator update, and we would like to figure out what's that matrix and what are its eigenvalues. Now, interestingly enough, you can also work out these eigenvalues by hand, just more linear algebra. So let's take our Laplacian. This tells us who talks to whom, calculate its eigenvalues, and put them in an increasing order. As a property of the Laplacian one, that gamma 0 is always 0. You notice all of those rows sum to 0 in there. Then you can show that the closed-loop eigenvalues, a plus bk, as before, a plus lc. Now each one of these is a bit different. A plus bk plus lc minus gamma 1 fh. Fh is the transmitter-receiver pair gain. And then all the way up to gamma n minus 1 fh. So if you had a plus bk plus lc, you would have uncontrolled confusion in there. Now communication lets you get control of the confusion, because you get to choose f and h, and you can think this looks like a pole placement problem. Choose f and h to make these eigenvalues nice. But you can only do this if gamma is not 0. Gamma is 0, you've lost control of those dynamics, and you have confusion in your system. So what does it take to make